In the unending quiet of the cosmos, amidst the silent waltz of galaxies and the slow burn of 1 trillion suns, time itself moves differently. It is not measured in heartbeats or the turning of a calendar page, but in the gravitational spin of colossal objects and the patient decay of atomic nuclei. Humanity, in its brief and brilliant existence, has only just learned to listen to this cosmic clockwork. And sometimes, in the faint signals we decipher from the void, we hear a ticking, a countdown, not to an end, but to a revelation. For decades, the scientists at NASA, our designated stargazers and celestial watchkeepers, have been pointing their most sophisticated instruments towards the heavens. They have been piecing together a story billions of years in the making, a narrative written in light and gravity. Now their models, refined by decades of observation and powered by supercomputers, are converging on a single point in our immediate future. A prediction has been made, not of gentle celestial wonder, but of something far more primal, a forecast for the year 2026 that touches upon the terrifying, untamable power that underpins our very existence. This is not a story about an asteroid or a distant planetary alignment. This is an alert concerning the fundamental forces that govern our home galaxy, a premonition of an event that will serve as a stark and brilliant reminder of the violent universe we inhabit. What NASA's calculations point to is an awakening, a detonation on a stellar scale, so close and so significant that it will briefly rewrite our night sky. It is a promise of fire, an echo from a cosmic ghost, and a window into the truly frightening possibilities that lurk in the Milky Way's dark and uncharted territories. The prediction is not for the end of the world, but perhaps for the end of our innocence about the universe in which we live. The stage for this celestial drama is a constellation that has captivated human imagination for millennia, Corona Borealis, the Northern Crown. It is a delicate semicircular jewel box of stars, a familiar landmark for navigators and dreamers alike. But within this serene celestial diadem resides a ticking time bomb, a binary star system known as T Coronae Borealis. To the casual observer, it is unremarkable, a faint point of light usually invisible to the naked eye. Yet this unassuming star is a cosmic predator, a recurring nova, a so-called blaze star that has a documented history of violent periodic outbursts. And according to the most current analyses of its behaviour, its next great eruption is imminent. The year 2026 sits squarely in the middle of the predicted window. This is not wild speculation. It is a forecast rooted in a pattern of violence that we have witnessed before. The last time T Coronae Borealis flared to life was in 1946. In the aftermath of a world war, as humanity looked towards rebuilding, the heavens offered their own sudden conflagration. The star, normally beyond the threshold of human vision, suddenly surged in brightness by a factor of nearly 1,500. It became as luminous as Polaris, the North Star, a brilliant temporary addition to the crown. For a few days it shone like a celestial beacon, before fading back into its customary obscurity, leaving astronomers with a renewed sense of awe and oppressing mystery. But the 1946 event was not its first recorded performance. We can trace its history further back into the dusty annals of astronomical history. In 1866, the Irish astronomer John Birmingham, a dedicated amateur skywatcher, was the first to officially document its dramatic transformation from obscurity to prominence. His report sent ripples through the scientific community, confirming that the heavens were not as static and unchanging as was once believed. There is even compelling, albeit more fragmented, evidence suggesting that medieval monks in Germany may have chronicled its outburst in the year 1217, describing a wondrous sign that shone brightly in the northern crown. This is the nature of T Coronae Borealis. It is a celestial sleeper agent, lying dormant for 80 years at a time, only to awaken in a blaze of glory that forces humanity to look up and take notice. What NASA and the global astronomical community have now achieved is the transition from historical record-keeping to active prediction. We are no longer just waiting for the flash, we are anticipating it. Scientists are monitoring the system with unprecedented intensity, watching for the telltale signs that precede the cataclysm. They are observing a specific precursor event, a subtle, pre-eruption dimming. This dimming, a faint shadowing of the system before it explodes, has been identified in the historical light curve data from the 1946 event. Seeing it again would be the final signal, the pulling of the cosmic trigger, and recent observations suggest this dimming process may have already begun. To truly comprehend the terrifying nature of what will happen in 2026, we must first journey into the heart of this bizarre stellar system, 3,000 light-years from Earth. It is not a single star, but a dangerously intimate pair. One partner is a red giant, a bloated dying sun in its twilight years. Its outer layers of hydrogen gas are tenuous, held loosely by a weakening gravitational grip. It is a venerable, swollen orb, nearing the end of its long life. Its companion, however, is a monster of a different sort entirely. It is a white dwarf, the collapsed, super-dense corpse of a sun that has already died. Imagine the entire mass of our own sun, compressed into a sphere the size of the Earth. Its gravitational pull is almost beyond comprehension. A single teaspoon of its material would weigh as much as a freight train on Earth. This grotesque disparity in their evolutionary states has created a parasitic, cannibalistic relationship. The white dwarf is a gravitational vampire. Its immense gravity mercilessly siphons hydrogen from the atmosphere of its bloated red giant companion. This stolen gas does not fall directly onto the white dwarf's surface. Instead, it is drawn into a swirling, superheated vortex known as an accretion disk, a spinning platter of incandescent plasma spiraling inwards towards its doom. Let us construct an analogy to grasp the sheer physics at play. Imagine a colossal hydroelectric dam, but one that contains not water, but pure energy and matter. The red giant is the vast, overflowing reservoir, its contents spilling over the edge. The white dwarf is the impossibly deep, narrow drain at the bottom of that dam. The accretion disk is the whirlpool, a vortex of accelerating material screaming as it is pulled towards the drain. For decades, for 80 years, this process continues relentlessly. Hydrogen gas, stripped from the red giant, accumulates on the surface of the white dwarf. It is a slow, steady snowfall of stellar fuel onto an already impossibly dense core. But this is not ordinary snow. The pressure and temperature at the white dwarf's surface are extreme. As the layer of stolen hydrogen grows deeper, the pressure at its base builds to unimaginable levels. It becomes a planetary-scale blanket of explosive potential. The weight of the accumulating gas pushes down, compressing the bottom layer until it reaches a critical flashpoint. That point is around 10 million degrees Celsius. At this temperature, a chain reaction begins. The hydrogen nuclei, forced together against their will, begin to fuse into helium. This is not the gentle, controlled fusion that powers a stable star like our Sun. This is a runaway, instantaneous thermonuclear detonation across the entire surface of the white dwarf. The resulting explosion is what we call a nova. It is a blast of such monumental force that it heaves the entire stolen atmosphere back out into space at speeds of thousands of kilometers per second. For a few days, this single, planet-sized stellar remnant can outshine 100,000 stars like our Sun. The searing flash of light and radiation from this event will travel across the 3,000 light-year gulf and arrive at Earth in or around 2026. We will see it as a new star, a sudden, brilliant interloper in the Northern Crown, and while it poses no direct physical threat to us from its immense distance, its appearance is profoundly, philosophically frightening. It serves as a visceral, naked-eye demonstration of the casual violence that is the norm in our galaxy. The serene, peaceful night sky is a comforting illusion. In reality, it is a shooting gallery, a cauldron of unimaginable energies where stars are being torn apart and detonated with a frequency that is difficult for the human mind to process. The blaze star of 2026 is a warning shot. It is a small, relatively benign example of the cosmic hazards that are a constant feature of our galactic environment, and it begs the question, if this is what a small stellar explosion looks like, what do the truly big ones, the genuinely scary ones, look like? To answer that, we must venture beyond the relatively gentle fury of a recurrent nova and into the realm of the true titans of cosmic destruction. The thermonuclear flash of T Coronii Borealis, as spectacular as it will be to witness, is but a flickering candle flame when compared to the true foundries of cosmic terror that lurk in the galactic dark. First, we must consider the Magnetar. The very name evokes a sense of immense power, and it is not an exaggeration. A magnetar is a type of neutron star, but one with a magnetic field of such staggering physics-bending intensity that it defies all earthly comparison. A typical neutron star is already an object of extreme properties. It is the crushed remnant left behind after a massive star collapses in a supernova. It is a city-sized sphere containing more mass than our Sun, so dense that its atoms have been squeezed into a solid ball of neutrons. A magnetar is what happens when this already extreme object is born with, or develops, a magnetic field 1,000 times stronger than that of a normal neutron star, and a quadrillion times stronger than Earth's own magnetic field. The numbers are so large they become meaningless. So let's use an analogy. The magnetic field of a common refrigerator magnet is strong enough to hold a piece of paper. The magnetic field of Earth is powerful enough to deflect deadly solar radiation and guide our compasses. The magnetic field of a magnetar from a distance of 100,000 kilometers could strip the information from every credit card on our planet. From that same distance, it would distort the electron shells in your body's atoms, effectively dissolving you into a cloud of unbound particles. Its power is not just immense, it is existentially hostile to the very structure of matter. These celestial abominations do not sit idle. Due to the titanic stresses their own magnetic fields exert on their crusts, they are prone to starquakes. These are fractures and realignments in the neutron star's solid outer layer, and they release bursts of energy that make a nova look like a firecracker. On December 27, 2004, humanity got a taste of this power. A magnetar named SGR 1806-20, located 50,000 light-years away on the other side of our galaxy, experienced a major starquake. In a single tenth of a second, it released more energy than our Sun produces in 150,000 years. This gargantuan pulse of gamma rays and X-rays blasted out across the galaxy at the speed of light. Even from that incredible distance, the effects on Earth were measurable and deeply unnerving. The wave of radiation was so intense that it saturated the detectors on multiple NASA satellites, including the Swift Observatory, momentarily blinding our eyes on the sky. It slammed into our planet's upper atmosphere, the ionosphere, causing a major disturbance and measurably altering its shape and density. It was a direct physical blow delivered from halfway across the Milky Way. Think about that. An event so far away that its light took 50,000 years to reach us still had enough power to physically affect our planet's atmospheric shell. What if such an event occurred closer? What if a magnetar lurked within, say, 100 light-years of Earth? The prediction for that scenario is truly apocalyptic. A full-scale magnetar flare from that proximity would obliterate our ozone layer in an instant. The resulting flood of hard radiation would sterilize the surface of our planet, boiling the upper layers of the oceans and likely causing a mass extinction event on a scale not seen since the formation of the planet. There is no warning, there is no defense. The blast travels at the speed of light. The first we would know of it is the moment it struck. And unlike T Coronii Borealis, we have no way to predict when the next giant flare from a nearby magnetar might erupt. We simply know that these objects exist, and they are the most powerful magnetic phenomena in the known universe. But cosmic threats are not limited to explosive radiation. Some of the most frightening dangers are entirely invisible, silent assassins moving through the interstellar void. Our galaxy is not a static collection of stars in neat, predictable orbits. It is a dynamic, chaotic place, a gravitational pinball machine that has been running for 13 billion years, and in that time, it has produced countless rogue objects, celestial bodies ejected from their home systems to wander eternally through the dark. Among these are rogue planets, rogue stars, and most terrifyingly of all, rogue black holes. It is now believed that our galaxy could be haunted by as many as 100 million stellar mass black holes. These are the remnants of colossal stars that have died, objects with a gravitational pull so absolute that not even light can escape. The The vast majority are likely locked in binary systems or orbiting the galactic centre, but simulations of galactic dynamics show that a significant number must have been ejected during supernova explosions or through gravitational interactions with other massive objects. They were flung out into the interstellar medium like cosmic cannonballs, travelling at incredible velocities, completely dark, completely silent, and utterly invisible to our telescopes. Finding such an object is one of the greatest challenges in modern astronomy. You cannot see a black hole directly. You can only detect its influence on the things around it. The primary method for hunting them is through gravitational lensing. As a rogue black hole passes in front of a distant star, its immense gravity bends the space-time around it, acting like a lens. This lens momentarily magnifies and brightens the light from the background star in a very specific, predictable way. It is a fleeting, single-event signal. Teams using the Hubble Space Telescope and ground-based surveys have been scanning millions of stars for these telltale flickers, and they have found them. Several candidates for rogue black holes have been identified, their masses and velocities estimated from the lensing data. They are out there. Their existence is no longer just a theory. So what would happen if one of these silent wanderers were to pass through our solar system? The common misconception is that it would suck us in. The reality is both more subtle and just as catastrophic. Unless it was on a direct collision course with the Sun, its primary weapon would be gravity itself. A stellar mass black hole, 5 to 10 times the mass of our Sun, entering the Oort cloud would begin to wreak havoc. It would gravitationally disrupt the orbits of trillions of comets, sending a deadly shower of them careening into the inner solar system, creating an impact scenario that would dwarf the one that wiped out the dinosaurs. If it passed closer, through the Kuiper belt or near the orbit of Neptune, the consequences would escalate dramatically. The finely tuned gravitational balance of our solar system would be shattered. The orbits of the outer planets, Jupiter, Saturn, Uranus and Neptune, could be destabilized. Jupiter, our solar system's great protector, whose gravity shields us from many incoming comets, could itself be thrown into a new, eccentric orbit. The most chilling possibility is a close pass to the inner solar system. The black hole wouldn't need to swallow the Earth, it would only need to nudge it. A slight gravitational tug, delivered at the right moment, could alter our planet's orbit. It could be pushed into a wider, colder orbit, plunging Earth into a permanent, irreversible ice age. Or it could be pushed into a tighter, hotter orbit, causing our oceans to boil away, transforming our world into a sterile, Venus-like hothouse. Or worse, it could be ejected from the solar system entirely, to become a rogue planet itself, freezing solid as it tumbles alone through the eternal, sunless night of interstellar space. The arrival of such an object would be almost without warning. We might detect its gravitational influence on the outer planets a few years or decades before its closest approach, but by then, it would be far too late to do anything. We would be passengers on a planet at the mercy of a gravitational phantom. The 2026 nova is a flash of light. A Magnetar flare is a blast of energy. A rogue black hole is a disruption of the very fabric of space and time that holds our world together. And this brings us to the heart of our galaxy, the ultimate source of both its structure and its potential for devastation. At the centre of the Milky Way, 26,000 light-years from our quiet suburban spiral arm, lies Sagittarius A star. It is a supermassive black hole, a gravitational singularity containing the mass of over 4 million suns. It is the anchor around which our entire galaxy revolves. For now, it is a relatively quiet giant. But we are beginning to understand the unimaginable violence that characterizes its immediate vicinity. Astronomers have been tracking a swarm of stars known as the S-stars that are locked in impossibly tight, fast orbits around this central monster. One star, S2, completes an orbit in just 16 years, reaching speeds of over 25 million kilometers per hour as it whips around its closest point to the black hole. Its motion has become a crucial laboratory for testing Einstein's theory of general relativity in an environment of extreme gravity. But recently, an even more extreme star has been discovered. Named S4716, it completes an orbit in a mere 4 years. At its closest approach, It comes within 100 times the distance from the Earth to the Sun, travelling at a staggering 8,000 kilometers per second, almost 3% of the speed of light. Watching these stars dance on the knife edge of oblivion is a profound experience. It is a direct view into an environment so hostile, so dominated by warped space-time and tidal forces that it strains the limits of our physical understanding. The scary part is not that Sagittarius A star will somehow reach out and consume us. It is far too distant for that. The fear comes from understanding that this central engine is not always dormant. Many other galaxies have what are called active galactic nuclei, or AGNs. In these galaxies, the central supermassive black hole is actively feeding on vast clouds of gas and dust, and even entire stars that venture too close. This process of consumption unleashes titanic amounts of energy, creating jets of radiation and high-energy particles that blast out from the galactic core for millions of light-years, sterilizing any worlds that lie in their path. Our galaxy's centre is quiet now, but it hasn't always been. Evidence from gamma-ray and X-ray telescopes has revealed the existence of two enormous, ghostly structures extending above and below the galactic plane, known as the Fermi Bubbles. These are the remnants of a colossal eruption from Sagittarius A star that occurred a few million years ago. Our galaxy's heart has a history of violence. What would happen if it were to reawaken? A large influx of gas, or the unlucky passage of a star cluster could reignite the beast. The resulting AGN would flood our section of the galaxy with deadly radiation, with potentially catastrophic consequences for life on Earth. We live in a calm period, a temporary truce, but the sleeping dragon at the centre of our Milky Way could stir at any time. The forces at play are millions of times greater than the nova that will grace our skies in 2026. These cosmic realities, the recurring nova, the Magnetar flare, the rogue black hole, the sleeping galactic core, force us to confront a deep and unsettling philosophical question. It is the question at the heart of the Fermi paradox. If the universe is so vast, why is it so silent? Where are all the other advanced technological civilizations? Perhaps the answer lies not in biology or sociology, but in astrophysics. Perhaps the universe itself imposes a great filter. It could be that life arises frequently, but that the galactic environment is simply too violent for it to survive long enough to achieve an interstellar presence. Civilizations may rise on their worlds, look to the stars, and then be extinguished by a Magnetar flare from a previously unknown neighbour. They might be gravitationally ejected from their own systems by a wandering black hole, or their entire region of the galaxy could be sterilized by the reawakening of their supermassive black hole. The universe may not be actively malevolent, but its baseline level of ambient violence could be so high that it effectively prunes the tree of life before its branches can ever reach for other stars. From this perspective, our own continued existence seems less like a certainty and more like an incredible stroke of luck. We are living in a quiet moment, in a relatively safe neighbourhood of a very dangerous city. The prediction for 2026 is therefore something more than just a fascinating astronomical event. It is a wake-up call. It is a gift of perspective. For the first time in 80 years, we will have the opportunity to see with our own eyes a star detonate. We can step outside on a clear night and witness a thermonuclear explosion thousands of light years away, a new point of light shining down on us from the Northern Crown. This is not something to be viewed on a screen or read about in a textbook. It is a direct, visceral connection to the immense and powerful forces that have shaped our cosmos. It is a memento mori on a galactic scale, a reminder of death and destruction, but also of renewal and the incredible cycles of matter and energy that make existence possible. The very atoms in our bodies, the carbon, the oxygen, the iron, were forged in the hearts of stars and flung out into the void by explosions far greater than the one we are about to witness. We are, in the most literal sense, the children of stellar cataclysms. The work of NASA and other scientific bodies is not to scare us, but to empower us with this knowledge. They are charting these dangers not to foster a sense of helpless dread, but to build a comprehensive understanding of our place in the universe. Each new discovery, each refined prediction, adds another piece to the puzzle. It allows us to appreciate both the incredible fragility of our world and the astonishing resilience of life that has managed to flourish here against such overwhelming odds. This knowledge is the greatest tool we have. It may one day be the key to our long-term survival, urging us to become a multiplanetary species, to spread the light of consciousness beyond this one beautiful vulnerable cradle. And so we return to the quiet anticipation of 2026. As the date approaches, telescopes all over the world, and in orbit above it, will remain fixed on that one unassuming point of light in Corona Borealis. They will be watching for the final dip in its brightness, the last deep breath before the plunge, and when it comes, the news will flash across the globe. It will be an invitation for all of us, for every person on this planet to go outside, to look up and to find the Northern Crown. There you will see it, a brilliant star-like beacon that was not there the night before. It is not an omen of doom. It is a messenger. It carries a story of cosmic hunger, of gravitational theft, and of thermonuclear fire. Its light is a 3,000-year-old echo of a drama that plays out countless times across the vastness of our galaxy. The truly scary thought is not that this explosion is happening. The truly scary thought is that this is one of the small ones, a minor firework in a gallery of galaxy-shattering bombs. The universe is not for us. It was not made with our safety or comfort in mind. It is a realm of magnificent, terrifying, and utterly indifferent power. The blaze star of 2026 will shine for a few precious days, a brief fiery message from the deep, reminding us of the grand, dangerous, and beautiful drama we have the profound privilege to be a part of. And it will remind us to cherish the quiet moments, the calm interludes, on our own small blue world, adrift in the magnificent and frightening cosmic sea. Look up on a clear, moonless night far from the glare of city lights. You will see it, a soft, shimmering river of stars flowing across the heavens. This is the Milky Way, our home. For millennia we have seen it as a symbol of peace, of constancy, a celestial roadway for gods and spirits. It feels serene, eternal, a comforting blanket of distant suns. But this placid appearance is a grand illusion. That gentle stream of light conceals a truth of unimaginable violence. It hides a secret kept in a chamber of dust and gas, 26,000 light-years away. If you trace that river to its densest, brightest point in the constellation Sagittarius, you are looking towards the heart of a maelstrom, a gravitational vortex of such profound power that it dictates the fate of our entire galaxy. You are looking towards a monster, and it is very, very real. This is the story of Sagittarius A star, the supermassive black hole at the centre of our galaxy. It is a tale of a cosmic leviathan, a phantom predator weighing more than 4 million of our suns, compressed into a volume smaller than the orbit of Mercury. It is an account of the generations of scientists who hunted this invisible beast, and a glimpse into a terrifying future that is written in the stars, a future where this sleeping giant may one day awaken. Our journey into this heart of darkness begins not with a telescope, but with an antenna, and with a persistent, inexplicable hiss. In the early 1930s, a young radio engineer named Karl Jansky was tasked by Bell Telephone Laboratories to investigate sources of static that were interfering with transatlantic radio communications. He built a remarkable contraption, a rotating antenna 100 feet long, which he mounted on Ford Model T wheels. It was nicknamed Jansky's merry-go-round. For months he listened. He catalogued the familiar crackle of distant thunderstorms and the hum of man-made interference. But there was another sound, a steady faint hiss that rose and fell once every 23 hours and 56 minutes. This was not a terrestrial day of 24 hours. This was a sidereal day, the time it takes for the Earth to rotate once relative to the distant stars. Jansky realised with a dawning sense of astonishment that the source of this static was not from our world. It was coming from space. He had unknowingly founded the field of radio astronomy. He traced the signal to its strongest point, the constellation Sagittarius. Jansky had found the first clue, the first whisper from the galactic core, but the world was slow to understand the magnitude of his discovery. For decades, the mystery of the galactic centre remained shrouded, both by our limited technology and by immense, impenetrable clouds of interstellar dust. This zone of avoidance blocked visible light, turning the galactic core into a forbidden kingdom, its secrets locked away from our sight. But radio waves, like Jansky's hiss, could pierce through that veil. As technology advanced, astronomers built more powerful radio telescopes, and their picture of the galactic centre grew sharper and stranger. They saw colossal filaments of magnetized gas, twisted like cosmic serpents. They detected the agitated motions of gas clouds, moving at bewildering speeds, orbiting something they could not see. In 1974, two astronomers, Bruce Ballack and Robert Brown, pinpointed an intensely bright and compact radio source at the very centre of the maelstrom. They designated it Sagittarius A star. The A for its intensity, and the asterisk, as Brown noted, because the discovery was so exciting, and the source itself was a purely mathematical representation of an exhilarating new puzzle in fundamental physics. The hunt for the monster now had a name. But what was it? A dense cluster of stars, a new exotic celestial object. The most radical and terrifying hypothesis was that it was a black hole, a concept so strange it seemed to belong more to science fiction than reality. A black hole is the final macabre triumph of gravity. It is what remains when a truly massive star dies, its core collapsing under its own weight so completely that it tears a hole in the very fabric of space-time. Imagine space-time as a vast, taut rubber sheet. A planet like Earth creates a small dimple. The Sun, a deeper one, which is why the planets orbit it. Now imagine a bowling ball so heavy it stretches the sheet infinitely downward, puncturing it completely. This is a black hole. It is not an object in space. It is a place where space itself has ceased to behave as we know it. It possesses a boundary known as the event horizon, a one-way door in the universe. Anything that crosses it, light matter information, can never escape. It is the ultimate point of no return. To prove that such a phantasmal object resided in our own galactic backyard was an astronomical challenge of epic proportions. You cannot see a black hole, you can only observe its devastating influence on everything around it. Proving its existence required a stakeout of cosmic proportions, one that would last for decades. This monumental task fell to two rival teams of astronomers, one in Germany led by Reinhard Genzel, the other in California by Andrea Ghez. Their mission, to watch the stars at the galactic centre and catch the monster red-handed. Their method was, in principle, quite simple, yet technically audacious. If a supermassive black hole was truly lurking there, then the stars closest to it should be orbiting at mind-boggling velocities, like planets in a frenzy around an invisible, hypermassive sun. Finding and tracking these stars, however, was akin to trying to spot a candle flame on the surface of the moon. The Earth's atmosphere, which allows us to breathe, is a formidable enemy to astronomers. Its constant turbulence blurs and distorts the light from distant stars, making sharp images of the crowded galactic core impossible. To overcome this, both teams pioneered the use of a revolutionary technology called adaptive optics. It is a work of scientific magic. A powerful laser is fired into the sky, creating an artificial guide star. Sensors measure how the atmosphere distorts this artificial star's light hundreds of times per second. A computer then calculates the precise distortion and sends signals to a flexible, deformable mirror in the telescope's path. This mirror contorts itself in real time, cancelling out the atmospheric blurring. For a fleeting moment, the view becomes as clear as if the telescope were in space. It is like looking at a coin at the bottom of a turbulent pond, and suddenly having the water become perfectly, miraculously still. Using this technique at the Keck Observatory in Hawaii and the Very Large Telescope in Chile, Genzel and Ghez began their vigil. Year after year, they captured fleeting, sharp images of the galactic heart, painstakingly plotting the positions of individual stars. These were the S-stars, a swarm of young, massive suns caught in the monster's grip. One star in particular, named S2, became their primary target. It was on a tight 16-year elliptical orbit around the unseen centre. As the years of observation accumulated, the data began to paint a terrifying picture. S2 was moving at astonishing speeds. At its closest approach to the centre, It blazed through space at over 25 million kilometers per hour, nearly 3% of the speed of light. It was being whipped around by a gravitational force of unimaginable intensity. There was no other explanation. The teams calculated the mass of the central object required to hold S2 in its orbit. The number was staggering: 4. 3 million times the mass of our Sun, and all of this mass had to be contained within a space smaller than our solar system. No star cluster could be that dense and that dark. It could only be one thing. The data from Genzel and Gez, the culmination of nearly 3 decades of work, was the definitive proof. It was the smoking gun. Humanity now knew, with observational certainty, that a supermassive black hole, a true monster, occupied the throne room of our galaxy. For this monumental achievement, they were awarded the Nobel Prize in Physics in 2020. They had made the invisible visible. But science is never content with inference. The next great challenge was to do the impossible, to take a direct photograph of the monster's silhouette. This was a task so audacious it required a telescope the size of a planet. The project was called the Event Horizon Telescope, or EHT. It was not a single instrument, but a global network of radio telescopes, from the deserts of Chile to the volcanoes of Hawaii, from Spain to the South Pole. They would all be synchronized by atomic clocks and pointed at Sagittarius A star simultaneously. The technique, known as very long baseline interferometry, is a marvel. By precisely combining the data from each distant telescope, astronomers could simulate a single virtual dish as wide as the Earth itself. This planetary-scale instrument would have the resolving power to see an orange on the Moon. It was the only tool powerful enough to discern the shadow of our black hole. The challenge was immense. Our black hole, though massive, is relatively small in the sky. Its event horizon appears about the same size as a donut left on the lunar surface. Furthermore, the gas swirling around Sagittarius A star is a turbulent, frenzied tempest, changing its appearance from minute to minute. Imaging it was like trying to take a clear photo of a spinning top in the middle of a blizzard. For years, hundreds of scientists and engineers from around the world worked on the project. They collected petabytes of data, so much that it couldn't be sent over the internet and had to be physically flown on hard drives from the various observatories to central processing centres. Then came the painstaking task of stitching it all together, of finding the faint ghostly signal of the black hole's shadow within a mountain of noise. In 2022, the world held its breath. The image was revealed. It was not a gaping black void, but something far more ethereal and profound. A glowing, blurry ring of superheated plasma, a cosmic donut of golden light, surrounding a dark central patch. That darkness was the shadow, the abyss itself. The light was from gas and matter, accelerated to near light speed and heated to billions of degrees as it spiraled into the maw. We were looking at the fiery gate of hell, the glowing rim of oblivion. We had photographed the unseeable. We had a portrait of our galaxy's monster. For now, Sagittarius A star is a sleeping giant. It is what astronomers call a quiescent black hole. Its feeding is sporadic, consisting of stray gas clouds and the occasional unfortunate star. But this tranquility is not guaranteed to last. The galactic centre is a dangerous neighbourhood. It is thousands of times more crowded than our peaceful stellar suburb. Stars, gas clouds, and other celestial bodies are constantly jostling for position, many of them on decaying orbits that will one day lead them to the monster. And when a supermassive black hole begins to feed in earnest, it awakens. It transforms into one of the most terrifying objects in the universe, an active galactic nucleus. Imagine our black hole not as a quiet drain, but as a cosmic volcano. When a large cloud of gas or a shredded star falls towards it, it doesn't just vanish. It forms a vast, swirling accretion disk. Friction and magnetic forces within this disk heat the material to temperatures hotter than the core of any star, causing it to blaze with the light of 1 trillion suns. The object at the centre of the galaxy would outshine the combined light of all the hundreds of billions of stars in the Milky Way. It would become a quasar, the most luminous phenomenon in the cosmos. Simultaneously, the immense magnetic fields twisted by the black hole's spin would act like a colossal particle accelerator. They would seize a portion of the infalling matter and redirect it, blasting it outwards from the poles in two stupendous jets of plasma travelling at nearly the speed of light. These jets would be galactic in scale, extending for tens of thousands of light years, far beyond the main disk of the Milky Way. They would be cosmic blowtorches of unimaginable power. If Sagittarius A star were to awaken in this manner, the consequences would be catastrophic. The radiation pouring from the galactic core would be so intense that it could sterilize life on any unprotected planet within thousands of light years. The powerful jets would plough through the galaxy, heating gas, disrupting star formation, and potentially scouring the atmospheres from worlds in their path. The night sky would be dominated by a new, terrifyingly bright star at its centre, a constant, searing reminder of the beast-renewed hunger. We are 26,000 light-years away, a distance that offers some protection, but the sheer scale of such an event is difficult to comprehend. Our galaxy's period of calm is not a permanent state, it is merely a phase. We have already witnessed a dress rehearsal for this kind of event. In the early 2000s, astronomers spotted a mysterious gas cloud named G2 on a direct collision course with Sagittarius A star. The scientific community was buzzing. They prepared their telescopes, expecting to see the black hole light up as it feasted on the cloud, a cosmic firework display for the ages. As G2 made its closest approach in 2014, it was stretched and distorted by the immense tidal forces of the black hole. It was a clear demonstration of the monster's gravitational power. The expected cataclysm, however, was more of a fizzle. The cloud seemed to mostly survive the encounter, and the black hole's brightness barely flickered. Scientists now believe G2 may have been denser than expected, perhaps containing a hidden star within it that held it together. But the event was a stark warning. The monster is there, it is hungry, and the galactic larder is full of potential meals. We were merely spectators to a near miss, a reminder of the latent power simmering at our galaxy's core. The true terror of Sagittarius A star is not just what it might do, but what it is inexorably destined to become. Our Milky Way is not alone in the cosmos. We are locked in a gravitational dance with our nearest large neighbour, the Andromeda Galaxy. Andromeda is larger than our own galaxy, and its supermassive black hole is a true titan, weighing over 100 million suns, and it is heading directly for us at a speed of 400,000 kilometers per hour. In approximately 4.5 billion years, our two galaxies will collide. This will not be a collision of solid objects. The spaces between stars are so vast that the two galaxies will mostly pass through each other like ghosts. But their gravitational fields will wreak havoc, flinging stars into new orbits, triggering a firestorm of new star birth and irrevocably scrambling their elegant spiral shapes. The night sky for any observer at that time would be a spectacle of unparalleled grandeur and horror, and at the heart of this cosmic merger, a far more violent drama will unfold. The two supermassive black holes, Sagittarius A star and Andromeda's behemoth, will feel each other's pull. They will be drawn together, initiating a final titanic waltz that will last for millions of years. They will orbit one another, spiralling ever closer, shedding vast amounts of energy in the form of gravitational waves, ripples in the fabric of space-time itself. These waves will be the most powerful ever produced in our local group of galaxies, a tsunami of distorted space travelling outward at the speed of light. As they finally merge, the event will be cataclysmic. The fusion of two such massive objects will release more energy in a single moment than all the stars in the universe combined. A new, even more monstrous black hole will be born, settling at the heart of the newly formed giant elliptical galaxy, which astronomers have nicknamed Milky. This new entity will be a graveyard of two majestic spirals, a chaotic jumble of stars ruled by a single, unimaginably vast singularity. This is the long-term forecast for our cosmic home, a future of collision, merger, and the creation of an even greater monster. But there are other, more immediate dangers that emanate from the galactic core. The gravitational dynamics near Sagittarius A star are a form of celestial billiards. Stars and black holes are constantly interacting, and sometimes an object can be slingshotted out of the core and into the wider galaxy at incredible speeds. These are known as hypervelocity stars, and we have observed them. They are bullets fired from the heart of the galaxy. More chilling is the prospect of hypervelocity black holes. Stellar mass black holes, the remnants of dead stars that get too close to Sagittarius. A star can be ejected with such force that they travel through the galaxy at millions of miles per hour. These are rogue agents of pure gravity, completely invisible, detectable only by the gravitational disruption they cause as they pass. A rogue black hole careening through our part of the galaxy is an improbable event, but not an impossible one. It is a silent, unseen threat, a ghost born from the chaos at the galaxy's centre. The sheer existence of Sagittarius A forces us to confront our own cosmic fragility. We live on a tiny protected rock, in a quiet, unassuming spiral arm, a galactic suburb far from the violent, chaotic metropolis of the core. Our existence is possible only because of this distance. We are shielded from the intense radiation, from the gravitational mayhem, from the monster itself. Yet, we are not separate from it. Its gravity is the anchor that holds our galaxy together. It is the conductor of the grand cosmic orchestra, in which our solar system is but one small player. The very force that could annihilate us is also the force that gives our galaxy its structure and shape. It is a profound paradox. This engine of potential destruction is also a fundamental component of our cosmic architecture. It reminds us that the universe is not a gentle, benevolent place. It is a realm of extremes, of forces that beggar the imagination, of creation and destruction, on scales we can barely model, let alone comprehend. To study Sagittarius, A star is to stare into the abyss, to confront the most extreme physics and the most powerful engine in our cosmic home. The journey from Jansky's faint hiss to the stunning image from the Event Horizon Telescope is a testament to human curiosity, ingenuity and persistence. We have hunted a ghost for nearly a century, using ever more sophisticated tools to probe a region of space that is fundamentally hostile and remote. We have succeeded in measuring its mass, plotting the orbits of its stellar captives, and even capturing its ethereal shadow. We have proven that the monster is real, but our understanding is still in its infancy. We do not know how these supermassive black holes formed in the early universe. We do not fully understand the physics of what happens beyond the event horizon, in the singularity where our laws of physics break down. We cannot predict with certainty when it will next awaken, and what the consequences will be. Every new piece of data opens up a dozen new questions. The scary reality of the monster in our galaxy is not simply that it is a destructive force, it is that it represents the raw, untamed nature of the cosmos. It is a constant reminder that we inhabit a universe that is dynamic, violent, and utterly indifferent to our existence. The serene river of stars we see in our night sky is just the calm surface of a deep and turbulent ocean. And in its depths, the Leviathan waits. We have seen its shadow, we have heard its gravitational whispers, and we know, with a mixture of terror and awe, that its story and ours are inextricably and eternally intertwined. There is no scream because there is no air to carry it. There is no wind rushing past your face. There is only a profound, impossible silence, a quiet so deep it feels like a physical presence wrapping itself around you. You are falling, and below you or perhaps in every direction at once it waits. It isn't a hole in the conventional sense, not a pit you can see the bottom of, but rather a perfect sphere of impossible blackness. It doesn't reflect light, it consumes it. It doesn't occupy space, it devours space, pulling the very fabric of the cosmos into its heart like an infinite drain. This is not a destination, it is an executioner, and you have an appointment that you cannot under any law of the known universe possibly miss. The journey towards this abyss may have taken millennia, a silent drift across the interstellar void. But the final moments, the ones that truly matter, will be over in a flash of agony so profound our language has no words for it. We have only a name, a deceptively simple, almost playful term for the most violent process in the cosmos, spaghettification. And for a human body, this transformation from organised matter into a stream of fundamental particles This ultimate dissolution takes place in less time than it takes to blink. 0.1 seconds. That is the duration of your annihilation. How can something so total, so absolute happen so fast? How can the universe, with all its elegant laws and sprawling timescales, conjure a monster that operates on the timescale of a snapping finger? To understand this cosmic guillotine, we cannot simply look up at the stars. We must look inward into the very architecture of reality itself, into the twisted geometry of space-time that Albert Einstein first glimpsed in his equations. For a century, we have chased these ghosts in our mathematics. Theoretical physicists, our generation's great explorers, have spent their lives mapping this treacherous invisible terrain, not with ships, but with the pure, cold logic of their minds. They speak of it with a unique mixture of reverence and terror. It is the ultimate laboratory, a place where the rules of our perceived reality are not just bent, but shattered into a million unrecognizable pieces. In their world of chalkboards and supercomputers, they have sent countless imaginary astronauts on this one-way journey, watching as the numbers that describe a human being mass height density are subjected to forces that beggar belief, and every single simulation ends the same way. With a symphony of annihilation played in 1/100th of a second. To begin to comprehend your fate, you must first unlearn what you know about gravity. You think of it as a force that pulls you down, the gentle anchor that tethers you to the earth. Here on the precipice of oblivion, gravity reveals its true terrifying nature. It is not a simple pull, it is a differential, a gradient, a difference in force so extreme it becomes a weapon. As you fall feet first towards the event horizon, the final luminous boundary of no return, the black hole's gravitational embrace is not uniform. The singularity at its heart, a point of infinite density, pulls on your boots, with infinitesimally more force than it pulls on the top of your head. On Earth, this difference, this tidal force, is gentle, raising the oceans in a soft, predictable rhythm. Here it is a cosmic rack, an instrument of torture built from the curvature of space-time itself. You feel it first as a strange, weightless tingling, a subtle, unsettling sensation of being pulled in two directions at once. It is not a pain, not yet, but a deep cellular wrongness. Your body, a magnificent machine evolved over billions of years to withstand the gentle gravity of a single planet, has no defense against this. It is an alien assault on your very structure. This is the moment before the snap, the breath, before the plunge. You cross the event horizon. There is no fanfare, no shimmering barrier. It is a silent mathematical threshold, a one-way membrane in the universe. From this moment forward, all paths, all possible futures lead in only one direction, inward. The light from the distant stars you left behind is now warped into a strange constricting halo above you, a final glimpse of the universe you can never return to. Below there is only the pure, featureless black. And now the stretching escalates with terrifying velocity. The gentle tingle becomes an insistent, powerful pull. It feels as though invisible, impossibly strong hands have seized your head and your feet and are beginning to pull slowly at first, then with exponentially increasing ferocity. The force is no longer just external, it is inside you. Your own skeleton becomes a battlefield. The tidal gradient is now so immense that every vertebra in your spine is being pulled away from the one above it. The distance is microscopic, but the force is planetary. Your joints held together by ligaments and tendons designed for running and jumping are the first to fail. Your ankles, your knees, your hips, they dislocate not with a pop, but with a silent catastrophic separation. Your arms are torn from their sockets. You are being unmade piece by piece. Yet this is just the overture. The true horror is far more fundamental. The tidal forces are now working on a smaller scale. They are not just pulling your limbs apart, they are pulling the individual cells of your body away from each other. The integrity of your tissues, the very fabric of your being begins to dissolve. Your skin, your muscles, your organs, no longer held in their familiar shapes by electromagnetic bonds, start to flow. You're becoming a river of biological matter drawn out into a long, thin stream. This is the moment physics transcends biology and becomes something akin to divine wrathful art. The forces grow stronger with every micron you fall closer to the singularity. What was once a body is now a stream of disconnected tissues tens, then hundreds of feet long, and still the process of division continues relentless and absolute. The tidal forces these gravitational talons now reach for the molecules themselves. The complex chains of proteins and amino acids that encode your existence are ripped asunder. The very water in your cells is torn into its constituent hydrogen and oxygen atoms. You're no longer you. You're not even a collection of organic parts. You're a flow of fundamental elements, a glowing, superheated filament of what was once a conscious being, accelerating towards the center. And this is where we find our 100th of a second, that final, incomprehensibly violent moment. In the last few microseconds of the fall, as your atomic stream approaches the singularity, the gravitational gradient becomes almost infinite. The force difference across a single atom is now greater than the strong nuclear force that holds its nucleus together. The universe's most powerful glue comes undone. In an instant, every single atom that made you is sheared apart. Protons, neutrons, electrons, all are liberated in a final cataclysmic burst. Your matter, which once looked up at the stars and contemplated its own existence, is reduced to a stream of fundamental quarks and leptons, a thin luminous thread pouring into the infinite density at the heart of the black hole. From the first dislocation of bone to the final shredding of atoms, the entire catastrophic cascade unfolds in roughly 1/10 of 1 second. Less time than a nervous twitch. Less time than the shutter speed of a camera capturing a child's smile. This brutal efficiency is not born of malice. It is the simple, elegant and terrifying consequence of Einstein's greatest insight, that gravity is not a force, but a curvature in the very geometry of space-time. You're not being pulled apart by some cosmic monster. You are being unwritten by the language of the universe itself. The space you are falling through is itself falling, flowing like a torrential river into the singularity. And as that river of space narrows and accelerates, anything caught in its current is inevitably stretched and squeezed into oblivion. This isn't just your body being destroyed, it is your dimension being compressed out of existence. Your three-dimensional form is being extruded through a one-dimensional nozzle. The physics that governs this process is both beautiful and merciless. It treats a star, a planet, or a human body with equal indifference. All are simply collections of matter to be deconstructed by the tidal teeth of the abyss. But there is a twist in this terrifying tale, a detail that adds another layer of cosmic dread to the experience. The speed and location of your destruction depend entirely on the kind of black hole you have chosen for your final descent. For a small stellar mass black hole, the collapsed corpse of a single giant star, the tidal forces at the event horizon are already astronomical. Spaghettification would happen to you before you even cross that threshold of no return, your body being ripped apart while you can still in principle see the outside universe. A swift if unimaginably painful end. But if your destination is one of the universe's true titans, a supermassive black hole, millions or billions of times the mass of our sun lurking in the heart of a galaxy, your fate is far, far stranger. These behemoths are so vast that their gravitational gradient at the event horizon is surprisingly gentle. You could in theory drift across their point of no return completely unharmed. You would feel nothing. For minutes, perhaps even hours, you would continue your fall into the darkness intact and for a terrifying moment still alive and conscious. You would be a ghost inside the machine, a traveller in a land from which no message can ever escape, witnessing firsthand the bizarre warping of space and time. But your reprieve is only temporary. The executioner has not forgotten you. As you continue your inexorable plunge deeper into the belly of the beast, the tidal forces will build slowly at first, then with the same catastrophic acceleration. Your spaghettification is not avoided, it is merely postponed, saved for a private viewing deep within the black hole's hidden sanctum. It is a death in a locked room the size of a solar system. This horrifying thought experiment forces us to confront the most profound questions we can ask. The process we've described is the destruction of your physical form, the disassembly of your matter. But what happens to the person that matter encoded? What happens to your consciousness, your memories, the unique pattern of electrical signals that constituted your mind? Does it simply vanish in that final fiery instant? Or does the bizarre physics of the black hole, where time itself is stretched to a standstill, from an outsider's perspective, preserve that information in some way we cannot yet comprehend? when you are stretched into a stream of atoms, is the story of your life somehow imprinted onto the event horizon itself, a cosmic hologram for eternity? This is not just a question of survival, it is a question that strikes at the heart of reality. Pitting Einstein's theory of relativity against the strange and ghostly laws of quantum mechanics. The 0.1 second destruction of your body is just the beginning of the mystery. It is the violent physical act that opens the door to a far deeper and more unsettling inquiry into the nature of time information and existence itself. To truly understand what it means to fall into a black hole, we must journey past the point of bodily annihilation. We must follow your ghost into the machine and dare to ask the ultimate question. What lies at the heart of the darkness? What if the fastest thing in the universe was not fast enough? Imagine a prison built not from steel or stone, but from the very shape of reality itself. A cage so powerful that its bars are the warped geometry of space-time, and its warden is gravity absolute and unforgiving. From this prison nothing can ever escape. Not a starship, not a planet, not a single particle of dust. Not even light, the absolute speed limit for all of creation, can break free once it has crossed the threshold. This is not science fiction. This is the chilling physical reality of a black hole, a place where our most fundamental laws of physics are pushed to their breaking point and beyond. To understand this ultimate cosmic abyss, we cannot begin with telescopes peering into the dark. Our journey must start 2 centuries ago in the mind of a quiet English rector, a man who saw the ghost of a black hole hiding within the elegant mechanics of Isaac Newton. His name was John Michell, a brilliant but reclusive natural philosopher living in an age of reason and revolution. In 1783, long before anyone had ever dreamed of bending space or slowing time, Michell engaged in a remarkable thought experiment. He lived in a Newtonian universe, a cosmos governed by a universal law of gravitation, a force that reached out across the void to pull objects toward one another. He also knew, thanks to Newton's other work in optics, that light could be conceived of as a stream of tiny particles, or corpuscles. Like any other particle, like a cannonball fired from the Earth, he reasoned that light must also be subject to gravity's relentless pull. From this simple, almost quaint set of assumptions, an astonishing conclusion emerged. Michell began to wonder about escape velocity. He knew that to escape the Earth's gravitational embrace, a cannonball must be fired at a tremendous speed, over 11 kilometers per second. If it travels any slower, it will inevitably fall back. He then asked a profound question. Could a celestial body be so massive and so compressed that its escape velocity would be greater than the speed of light itself? He meticulously calculated that a star 500 times wider than our Sun, but with the same density, would have such an immense gravitational field that its own light would be unable to climb out. The light particles fired from its surface would rise for a moment before being rained in, falling back to the star like a fountain spray. The star would become invisible to the distant universe. It would be a dark star, a star cloaked in its own gravitational shroud. For Michell, this was a fascinating but purely theoretical curiosity, a phantom born from the cold logic of Newtonian equations. He had no way of knowing that he had brushed against one of the most extreme and violent concepts in the entire cosmos. His idea, published in a letter to the Royal Society, was largely forgotten, a footnote in the history of science. Over a decade later, the brilliant French mathematician Pierre-Simon Laplace, completely unaware of Michell's work, independently arrived at the very same conclusion. He too envisioned these core obscures or dark bodies populating the heavens, forever hidden from our view. But for the scientific establishment of the 19th century, the idea was simply too bizarre, too far removed from the observable clockwork of the solar system. The wave theory of light became dominant, and the concept of light as a particle that could be pulled by gravity fell out of favour. The dark star, this gravitational ghost, faded back into the intellectual shadows, waiting. It would wait for more than a century for a new kind of physics, a new understanding of reality itself to be born from the mind of a German patent clerk. Albert Einstein did not set out to find monsters in the dark. He was obsessed with a deep and beautiful paradox. For over 200 years, Newton's law of universal gravitation had reigned supreme. It described how a planet orbits a star with stunning precision, yet it held a secret absurdity. According to Newton, gravity was a force that acted instantaneously across any distance. If our Sun were to suddenly vanish, Newton's equations predicted that Earth would instantly fly off its orbital path into the cold darkness. But Einstein's own special theory of relativity, published in 1905, had already established a cosmic speed limit, the speed of light. Nothing, not even information, could travel faster. Gravity could not be instantaneous. Newton's elegant law, the bedrock of physics for centuries, had to be wrong, or at the very least incomplete. For 10 years, Einstein wrestled with this problem in a titanic intellectual struggle. His quest was to reimagine gravity to discover its true nature. The breakthrough, when it came, was a complete demolition and reconstruction of our concepts of space and time. In his general theory of relativity, unveiled in 1915, Einstein declared that gravity is not a force at all. It is not an invisible rope pulling you down to your chair. Gravity, he proposed, is the consequence of mass and energy warping the very fabric of the universe. He asked us to picture space and time not as a static, empty stage on which the cosmic drama unfolds, but as a dynamic, flexible entity in its own right, a four-dimensional fabric he called space-time. Imagine this fabric stretching to infinity in all directions. A massive object like our Sun doesn't pull the Earth with a mysterious force. Instead, its immense mass creates a deep depression, a gentle curve in the surrounding space-time, much like a heavy bowling ball placed on a stretched rubber sheet. The Earth in its orbit is not being pulled. It is simply following the straightest possible path through that curved, distorted geometry. It is coasting along the rim of the valley created by the Sun. In Einstein's universe, planets are not prisoners of a force. They are cosmic marbles rolling along the contours of a warped reality. This was a revolution in thought so profound it shook the foundations of our worldview. It replaced the force of gravity with the shape of space, a concept as beautiful as it was bizarre. And locked within the dense labyrinthine mathematics of his new theory were equations that described how this space-time fabric could be bent, stretched and twisted. He had given humanity the rules, but he had not yet foreseen the monsters those rules would allow. The world was at war. As Einstein published his masterpiece in Berlin, a German astrophysicist named Karl Schwarzschild was serving on the Russian front, calculating artillery trajectories amidst the deafening roar of combat. Despite the hellish conditions, Schwarzschild obtained a copy of Einstein's work and was immediately captivated. While Einstein himself had only managed to find approximate solutions to his own ferociously complex equations, Schwarzschild, in a feat of pure intellectual brilliance, found an exact solution. In the mud and chaos of the battlefield, he calculated the precise geometry of space-time around a single, spherical, non-rotating mass. He mailed his results to an astonished Einstein, who presented the work on his behalf to the Prussian Academy of Sciences. It was the very first confirmation that Einstein's abstract theory could yield concrete physical predictions. But Schwarzschild's solution contained something deeply unsettling. His mathematics described how space-time curves around an object like a star. As you get closer to the star, the curvature becomes more pronounced. This was expected. But the equations also held a prophecy. They predicted that if you could compress any amount of mass into a sufficiently small volume, the curvature of space-time would become infinite. The structure of reality itself would collapse inward, pinching off into a point of zero volume and infinite density. Schwarzschild had not just rediscovered Michel's dark star, he had given it a terrifying new identity forged in the language of warped space-time. He had calculated the precise boundary of this object, a critical threshold now known as the Schwarzschild radius. For an object with the mass of our Sun, this radius is a mere 3 kilometers. For the Earth, it is the size of a small marble. This boundary is not a physical surface you could touch. It is far more profound. It is a one-way door in space-time. It is the event horizon. Crossing it is not a matter of engine power or velocity. It is an inevitability written into the geometry of the universe. Inside the event horizon, the curvature of space-time is so extreme that all possible paths, every single trajectory you could possibly take, lead in only one direction, inward toward the center. The future itself points to the core. Imagine you are in a river paddling a canoe. Far upstream, the current is gentle, and with enough effort you can paddle against it and return to the bank. But as you drift downstream, the river narrows and the current quickens. Soon you hear a roar. You've drifted too close to the edge of a colossal waterfall. At this point, the water is rushing over the precipice faster than you could ever hope to paddle. No matter which way you turn your canoe, no matter how hard you fight, you and the water you're in are going over the edge. The event horizon is that final roaring edge of the waterfall. It is the precise point where the required escape velocity equals the speed of light. But in the language of relativity, it is more accurate to say that it is the point where space-time itself is flowing inward into the black hole faster than light. Since nothing can travel faster than light through space, once you cross that threshold, escape is a geometric impossibility. You are caught in a current of collapsing reality, a current that drags you inexorably toward your fate. And what is that fate? What lies at the destination of this one-way journey? Schwarzschild's equations point to a place that defies all logic and language. They point to the singularity. The singularity is the heart of the black hole, the point where all the mass that has ever fallen in is crushed into an infinitesimally small space. Here, according to general relativity, the curvature of space-time becomes infinite. Density becomes infinite. The gravitational pull becomes infinite. It is a place where space and time as we understand them cease to exist. Our laws of physics, the very tools we use to describe the universe, break down completely. The singularity is not a place in the universe. It is an end to the universe. It is a cosmic dead end, a wall at the edge of reality. For decades, many physicists, including Einstein himself, refused to believe that such an object could actually form in nature. They saw Schwarzschild's singularity as a mere mathematical anomaly, a flaw in the equations that would be resolved by a more complete theory. They couldn't accept that the cosmos would permit such a monstrous physics-breaking object to exist. But the universe, we have learned, is under no obligation to conform to our sense of reason or comfort. We now know that black holes are real. We have seen the shadows they cast against glowing clouds of gas. We have watched stars orbit these points of utter blackness, their paths dictated by the unseen gargantuan masses within. We have even detected the faint gravitational ripples, the echoes in space-time from the violent collisions of two black holes in the distant universe. The ghosts of Michel and Laplace have become terrifyingly real, scattered throughout the cosmos by the millions. We stand on the precipice of understanding, staring into an abyss from which no information can return. We have established the existence of this ultimate prison. We have mapped its one-way gate, the event horizon, and we have glimpsed the mathematical horror of the singularity that lies within. We know that the gravity near these objects is the most powerful force in the cosmos. This leaves us with the most intimate and terrifying question of all. We understand the destination, but what about the journey? What would actually happen to you if you were to take that fall? We often imagine being crushed by the immense gravity, flattened into oblivion. But the truth is far stranger, more specific, and infinitely more violent. Before you ever reach the singularity, before you even cross the event horizon of a smaller black hole, your body will be subjected to a force so perverse and so powerful that it will execute you in the most brutal way imaginable. It is not gravity itself that will kill you. It is the difference in gravity. What are these cosmic forces of separation, these gravitational tides so extreme they can stretch and tear the very atoms of your being across the fabric of space? To find the answer, we must now move beyond the elegant geometry of space-time and into the raw physical mechanics of your final, terrifying moments. We must understand the force that will shred you into a stream of fundamental particles in less than the blink of an eye. And so you fall. You're captured a mote of dust in an infinite cosmic river, pulled by a current of space-time so powerful that light itself cannot escape its flow. In the previous chapter of our journey, we confronted the raw, absolute nature of this gravitational pull, a force that bends worlds and devours stars. We imagined it as a simple monolithic force, a cosmic drain pulling everything toward a single inescapable point. But to truly comprehend your fate, to witness the horrifying mechanics of your final moments, we must now discard that elementary image. The truth of gravity, especially the gravity reigning here at the edge of oblivion, is far more insidious, more intimate, and infinitely more violent. Its true weapon isn't the uniform pull that draws you in. It's the difference in that pull from one inch to the next. Its killing power lies not in its strength, but in its gradient. To understand this, we must first return home to our own gentle world and look to the patient rhythm of the oceans. Twice a day, coastlines around the globe watch the sea draw a deep breath and then exhale. This is the tide, a phenomenon so familiar we rarely consider the colossal forces at play. We are taught that the moon's gravity pulls on the Earth, creating this aquatic pulse. But that explanation is deceptively simple, missing the crucial detail. The moon does not pull on the Earth as a single solid object. It pulls on every single particle of our planet, every mountain, every ocean droplet, every atom in your body, and critically it pulls more strongly on the parts of the Earth that are closer to it. The water on the side of the Earth facing the moon is pulled with slightly more force than the solid core of the planet beneath it. This differential pull causes the ocean to bulge outward, creating a high tide. But what about the other side of the planet? The side facing away from the moon. There the ocean also bulges. Why? Because here the moon's gravity is at its weakest. It pulls on the solid Earth more strongly than it pulls on the distant water, effectively leaving that water behind. The result is a second opposing high tide. Our planet is constantly gently being stretched along this Earth-Moon axis. It is a planetary scale massage, a subtle elongation orchestrated by a whisper of gravity from 250,000 miles away. These are tidal forces. On Earth, they are benign, a source of poetry and power. They are the gentle ghost of a far more terrifying cosmic principle. For what the moon does delicately to our oceans, a black hole does with unimaginable brutality to the very fabric of matter. The principle is identical. The scale is apocalyptic. Let us leave the familiar shores of Earth and travel to a place where this principle is written in fire and stone, Jupiter's innermost Galilean moon, Io. From a distance, Io is a marble jewel of sulphurous yellows, reds and blacks, but this beauty is born of pure torment. Io is the most volcanically active body in our entire solar system. Its surface is a tortured canvas of colossal volcanic plumes, vast plains of molten rock and mountains heaved miles into its thin atmosphere. This is not the familiar geothermal heat of a planet's core driving a few isolated volcanoes. This is the entire world being continuously broken and melted from the inside out. Io is trapped in a gravitational tug-of-war between the colossal mass of Jupiter and the rhythmic pulls of its neighbouring moons, Europa and Ganymede. As it orbits, it is squeezed and stretched by Jupiter's immense gravitational field like a cosmic stress ball. The side of Io facing Jupiter is pulled with immensely more force than the side facing away. The difference in that pull across Io's 2,000-mile diameter is so extreme that its solid crust rises and falls by over 300 feet with every orbit. Imagine the entire landscape mountains and all heaving up and down by the height of a skyscraper every 42 hours. This relentless flexing generates an incredible amount of friction, deep within the moon's interior, melting its mantle into a global ocean of magma. The spectacular volcanic eruptions we see are just the surface expression of this deep, agonizing torment. Io is a world being torn apart by tidal forces. It is a visceral system-scale demonstration of what happens when the gentle stretching we see in our oceans is amplified by a true gravitational monster. It is a warning, a preview of the physics that now governs your own descent. Because where you're going, the forces that disfigure a world are compressed to the scale of a single human body. To grasp the terrifying intimacy of this process, let's bring the scale down to something human. Imagine you and a fellow astronaut are on a spacewalk tethered together, and you have both through some catastrophic error begun to fall toward a small stellar mass black hole. You are falling feet first. At first, the sensation is one of weightlessness, the classic illusion of freefall. You feel nothing, but the laws of physics are already at work signing your death warrant. The black hole's gravity, governed by the inverse square law, intensifies exponentially with proximity. Your feet being just 6 feet closer to the singularity than your head are experiencing a measurably stronger gravitational pull. At a great distance, this difference is trivial, smaller than the variance you'd feel standing on a flight of stairs on Earth. But the tidal force, this differential force, doesn't follow the inverse square law. It obeys a far more savage rule, the inverse cube law. This is a critical distinction, and it is the secret to the black hole's destructive power. As you halve the distance to the singularity, the overall gravitational pull on your centre of mass quadruples. But the tidal force, the stretching force between your head and your feet, doesn't just quadruple. It increases by a factor of 8. Every metre you fall closer, the disparity in the pull grows with breathtaking, catastrophic speed. Soon you would feel it, not as a pull, but as a tension. It would start as a subtle, unfamiliar ache in your joints, as if you'd been hanging from a pull-up bar for too long. The tether connecting you to your fellow astronaut would grow taut. The person falling slightly ahead of you, closer to the black hole, would begin to accelerate away, the tether straining under a load it was never designed to bear. This is the gravitational differential engine at work. It is not pulling you together. It is a force of separation. The atoms in your boots are being pulled away from the atoms in your shins. The bones in your legs are being pulled from their sockets in your pelvis. Your spine, a column of individual vertebrae, is being subjected to an impossible tension, each segment pulled more forcefully than the one above it. You are being placed on a cosmic rack designed by the universe itself, and the force is not just vertical. As you're stretched, another aspect of the tidal force comes into play. While your head and feet are pulled apart along the line of your fall, the rest of your body is being squeezed from the sides. Gravity is pulling every particle of your being toward the single, infinitesimal point of the singularity. Imagine lines radiating from that point out toward you. The lines hitting your left shoulder and your right shoulder are not perfectly parallel. They are converging. This convergence applies a colossal compressive force, squeezing your body from all sides, crushing your shoulders inward, flattening your torso. You're being simultaneously stretched and compressed, pulled longer and squeezed thinner. The process has a name, a term coined by astrophysicists that is both clinically descriptive and viscerally horrifying: spaghettification. Before you ever reach the event horizon of this stellar mass black hole, long before the point of no return where light itself is trapped, these tidal forces would become insurmountable. The ache would become an unbearable strain, then a sharp, tearing agony. The delicate structures of your body, evolved for the gentle, uniform gravity of a small planet, are simply no match for this focused violence. The human frame can withstand tremendous compressive forces. We can survive astonishing impacts, but our tensile strength, our ability to resist being pulled apart, is pathetically weak. Your body would begin to fail at the molecular level. Your skin, your muscles, your organs, your very bones would be stretched past their breaking point. First, your joints would dislocate. Your limbs pulled with more force than your torso would be torn from their sockets. The integrity of your skeleton would fail, your spine elongating and then snapping. Your circulatory system, under the immense strain, would rupture. But the process wouldn't stop there. The tidal forces continue to increase their power, growing by the inverse cube of the distance. The very tissues of your body, now unmoored from the skeleton, would be drawn out into long, thin filaments. Even the cells themselves would be warped, their membranes stretched until they burst. In the final imperceptible fraction of a second, the bonds holding molecules together would be overwhelmed. The fundamental forces of chemistry would surrender to the raw power of gravity. Your body would cease to be a biological entity. It would be rendered into a thin, glowing stream of constituent atoms, a trail of incandescent plasma, a few atoms wide and perhaps miles long, accelerating toward the event horizon. All of this, from the first subtle ache to your atomic disintegration, would happen in the blink of an eye. For a stellar mass black hole, your destruction is not an event that takes place inside the abyss. It is the brutal toll you must pay just to knock on its door. The event horizon is a finish line you would never reach in a recognizable form. But what if the black hole were different? What if it were not a mere stellar mass object, but a supermassive behemoth? Millions or even billions of times the mass of our sun, lurking in the heart of a galaxy. Here the story changes in a profound and terrifying way. The sheer size of a supermassive black hole alters the geometry of its gravitational field. Because its event horizon is so enormous, stretching for millions of miles, the curvature of space-time at its edge is much, much gentler. The inverse cube law still applies, but you're so far from the central singularity, even as you approach the horizon, that the tidal forces are for a time survivable. The gradient of gravity is spread out over a much larger distance. For a supermassive black hole like Sagittarius A, the monster at the centre of our own Milky Way, the stretching force at the event horizon, would be less than that which you feel on Earth. You could cross the boundary, the point of no return completely intact. You would sail past the cosmic veil, the last point from which a message could ever escape, feeling nothing more than the serene sense of weightless freefall. You would be alive and for a few moments perhaps even conscious inside the black hole. The universe outside would be gone from your view, its light, unable to follow you across the threshold. You would be utterly and completely alone, cut off from all of space-time. But your reprieve is temporary. The singularity still awaits. Inside the event horizon, the journey continues, and the tidal forces you so gently bypassed now begin to build with a ferocity that dwarfs anything a lesser black hole could produce. The fate of spaghettification is not avoided. It is merely postponed, reserved for the final act of your journey within the abyss itself. Whether you are torn apart in a flash of agony outside a small black hole, or granted a few moments of eerie tranquility before your annihilation inside a large one, the culprit is the same. It is not the simple brute force pull of gravity that seals your doom. It is this far more elegant, far more terrifying principle, the relentless, irrefutable fact that in the domain of a black hole, no 2 points in space experience the same reality. It is the cosmic shear, the differential pull across the infinitesimal space separating one atom from its neighbour. This is the force that unmakes matter, the gravitational scalpel that will dissect you with inhuman precision. And as you continue your fall, this is the force that is now beginning to awaken, to take notice of your presence, to measure the distance from your head to your feet, and to prepare its inexorable final judgment. The quiet hum of the cosmos has vanished, replaced now by a low resonant thrum that you feel more than you hear. It's a vibration in your very bones, a signal that the abstract laws of physics we discussed are becoming a terrifying, tangible reality. The gentle, inexorable pull we spoke of is no longer so gentle. It is becoming insistent, a preference. The black hole is no longer just pulling you in. It is beginning to dissect you from a distance, using gravity as its scalpel. You feel an unnerving sensation, a faint but persistent tugging at the edges of your body. It is not the feeling of acceleration of being dragged uniformly forward. This is something far more sinister. Imagine for a moment that every single atom in your being has a tiny invisible cord attached to it, each one leading directly to the singularity. Now imagine the cords attached to your feet are being pulled with immensely more force than the ones attached to your head. This is the dawn of the tidal force, the universe's most extreme stretching rack. The difference in gravity across the mere 2 meters of your height, a value that was infinitesimal just moments ago, is now growing exponentially with every kilometer you fall. It is a silent mathematical predator, and its grip is tightening. At first it might feel like a strange pins and needles sensation, a phantom limb being pulled, but soon that tingling sensation becomes a deep wrenching ache in your joints. Your spine, a marvel of evolutionary engineering designed to withstand the crushing gravity of a planet, feels a new kind of stress, not compression, but tension. A relentless longitudinal pull that seeks to separate each vertebra from its neighbour. You're on a gravitational gradient so steep it could be measured across your own form. Your body, which has only ever known the uniform gravity of Earth, is now a complex instrument measuring the terrifying curvature of space-time. Every cell is screaming a different number. The pull on your ankles is measurably painfully stronger than the pull on your knees. The force on your heart is significantly less than the force on your pelvis. This differential is the key. It is the mechanism of your undoing. Your entire existence has been governed by forces that hold you together. The powerful electromagnetic bonds between your molecules, the cohesive strength of your tissues, the structural integrity of your skeleton. These are the forces of life, the glue that maintains the intricate architecture of a human being against the chaos of the universe. For your entire life they have been more than enough. They have held you together through impacts, illnesses, and the simple, constant pressure of Earth's atmosphere. But you are now entering a realm where the rules have been rewritten by a monster. The black hole does not care about your biology. It does not recognize the chemical covenants that define you. It pits the most powerful force in the cosmos, gravity, against the delicate bonds of your own matter. This is a battle you were never meant to win. We can even calculate the breaking point. Scientists call it the Roche limit, the distance at which the tidal forces of a celestial body will rip apart another object held together by its own gravity. A moon that wanders too close to its planet is a classic example, torn asunder to form a beautiful tragic ring system. But you are not a moon. You are not held together by your own feeble self-gravity. Your form is maintained by the far more robust strength of your biological materials. Your bones have a specific tensile strength, the amount of stretching they can endure before they snap. Your skin, your muscles, your tendons, they all have a measurable elasticity, a point beyond which they will tear. We can therefore define a new kind of boundary, a grim perimeter in space, your personal Roche limit. It is the line you're now crossing, the invisible threshold where the black hole's differential pull becomes greater than the molecular forces holding your body intact. The transition is not gentle. It is a catastrophic, instantaneous failure. One moment you're a human being contorted in agony. The next you're a process, a demonstration of physics. The first thing to fail would likely be your largest, most rigid structures. Your femur, one of the strongest bones in your body, capable of withstanding thousands of pounds of compressive force, is now subjected to a tension it was never designed for. It does not bend, it shatters. The sound, were there any air to carry it, would be a sharp percussive crack. But there is only silence and the horrifying tactile sensation of your own body coming apart. Your spine, already stretched to an impossible length, disarticulates. The vertebrae, once a beautifully stacked column, are pulled away from each other, severing the spinal cord within. All neural communication between your brain and the lower half of your body ceases. You would be mercifully perhaps numb from the waist down, though the agony in your torso and head would be all-consuming. Simultaneously, another equally violent process is underway. While the tidal force is stretching you along the line towards the black hole, it is also compressing you from the sides. The same gravitational differential that pulls your head and feet apart also pulls every particle of your being toward the center line of your body. Imagine being in a room where the walls are closing in at the same moment the ceiling and floor are moving apart. It is a cosmic vice grip. Your shoulders are crushed inward, your ribs snapping and folding as your chest cavity collapses. The pressure becomes so immense that the very fluids in your cells are squeezed out. Your body, a vessel of water and complex chemistry, is being wrung out by the fabric of space-time itself. You are being stretched and squeezed into a new horrifying shape. The process accelerates with blinding speed. The failure of your skeletal system triggers a cascade. With your bones broken and pulled apart, your muscles and ligaments, no longer anchored, tear like wet paper. Your skin, stretched beyond its limits of elasticity, rips open. Your internal organs, no longer contained by the abdominal wall or protected by the rib cage, are pulled from your body and elongated into grotesque ribbons of tissue. It is not an explosion, a chaotic spray of biological matter into the void. It is a terrifyingly orderly deconstruction. Every piece of you is meticulously and violently drawn out into a long, thin strand following the gravitational lines of force directly toward the singularity. You are no longer a complex three-dimensional being. You are becoming a one-dimensional line pointed at the heart of the abyss, and the black hole is not finished with you. Your destruction transcends the merely biological. The tidal forces that dismantled your body continue their work on a smaller, more fundamental scale. The long chains of proteins and polymers that formed your tissues are now subjected to the same differential pull. The chemical bonds holding those molecules together, the very foundation of your organic chemistry, are the next to break. The carbon, hydrogen, oxygen, and nitrogen that composed you are stripped from their complex arrangements. Hemoglobin, DNA, adenosine triphosphate. The intricate molecules of life are unraveled, their atoms pulled apart by the irresistible gravitational shear. You have ceased to be biology. You're now just chemistry, a flowing stream of dissociated elements. Even this is a temporary state. The tidal forces continue to escalate, reaching down to the next level of reality. They grasp the atoms themselves. An atom is a durable thing, a nucleus of protons and neutrons orbited by a cloud of electrons, all bound by the powerful electromagnetic force. For billions of years, the atoms that make up your body have remained stable, participating in countless chemical reactions, forming stars, planets, and eventually you. But here on the doorstep of infinity, even the atom finds its master. The tidal force across the infinitesimal diameter of a single atom becomes significant. The gravitational pull on the side of the atom closer to the black hole is stronger than the pull on the far side. The atom itself begins to stretch. The electron cloud is warped, distorted into an ovoid shape. The nucleus is pulled one way, the electrons another. The electromagnetic force, the second strongest force in nature, finally gives way. The electrons are stripped from their nuclei. What was once a human being is now a stream of plasma. You are a thin, incandescent filament of protons, neutrons, and electrons glowing with the heat of your own disintegration. This ribbon of matter, a spectral ghost of your former self, continues to accelerate toward the event horizon. Astronomers have a name for this. They call it a tidal disruption event. We have seen this happen from unfathomable distances when an unlucky star wanders too close to a supermassive black hole. We watch through our telescopes as the star is pulled into a long, brilliant noodle of gas before being consumed. What you're experiencing is the same cosmic phenomenon scaled down to the intimate, horrifying level of a single human body. You have become your own personal constellation of death, a momentary streak of light against the ultimate darkness. Your constituent particles, once organised into a thinking, feeling being, are now just fuel and offering to the singularity. This entire cataclysm, this complete and utter annihilation of your physical form from skeleton to subatomic particle, unfolds with a speed that is almost impossible to comprehend. The title of our journey is not hyperbole, it is a horrifying calculation. In the ferociously steep gravitational well of a stellar mass black hole, the region where the tidal forces escalate from merely painful to utterly unsurvivable is incredibly narrow. You're falling through this lethal zone at a significant fraction of the speed of light. Let's pause the simulation for a final, terrible moment of clarity. The distance from the point where your bones begin to break to the point where your atoms are ionized is traversed in an almost immeasurably short span of time. We can calculate it. The time it takes for the tidal force to exceed the tensile strength of your body and then overwhelm the electromagnetic force holding your atoms together, all while you fall at relativistic speeds. The result is approximately 1/10 of a second, 0.1 seconds, less time than a single human heartbeat, faster than a conscious thought can form. One moment you are a being of immense complexity and history, and in the next flicker of existence you are an ionized stream of matter plunging into darkness. There is no time to scream, there is no time to process the unimaginable pain or the existential horror of your own unmaking. The universe does not grant you the mercy of a final moment. Your end is not a narrative. It is a physical event as swift and impersonal as a lightning strike. Your entire life, your thoughts, your memories, your consciousness, all embodied in a physical structure that is erased from the universe in a flash of gravitational violence. And the most profound, the most unsettling part of this entire sequence, it has all happened outside the black hole. You have not yet crossed the event horizon. This complete destruction, this reduction of a human being to a plasma stream is merely the prelude. It is the terrible price of admission. You have been killed by the journey, not the destination. The stream of particles that was once you continues its inexorable fall, a glowing testament to the power of gravity. It is this stream, this ghost of matter, that will now cross the final boundary, the one from which not even light can escape. The question that remains suspended in the silent void is what happens next. What becomes of this fundamental information, this atomic echo of a life when it finally slips beyond the veil and falls forever into the singularity? And so, the deed is done. The magnificent, intricate vessel that was a human body, a walking, thinking miracle of chemistry and electricity, is gone. It has been unwritten from the book of life, its story violently erased by the savage grammar of gravity. What remains is not a corpse, but a legacy, a fleeting, luminous epitaph written in the language of fundamental physics. You are now a river of incandescent plasma, a stream of constituent atoms stretched into a miles-long filament, arcing downwards at an impossible speed. This celestial contrail, this final fleeting monument to a life, glows with the furious energy of its own annihilation. It is a searing thread of light, pulled thin by the relentless loom of space-time plunging toward the blackness that commanded its creation. For a moment, this stream is all that is left of you, a fiery testament hurtling into the void. But here at the very precipice of oblivion, a final bewildering schism occurs. Reality itself, which we so confidently assume to be a single shared experience, bifurcates. It splits into two irreconcilable truths, two stories being told about your final moments. One story is told by the universe you left behind. The other is told by the atoms that carry the last vestiges of your being, and they could not be more different. Let us imagine a friend, a steadfast companion stationed at a safe distance, watching your descent through the lens of an impossibly powerful telescope. For them, for the entirety of the observable cosmos, your fall does not accelerate into a swift, merciful end. Instead, something profoundly strange begins to unfold. As your atomic stream approaches that sharp, dark edge in space, the event horizon, it appears to slow. Not as if it were hitting the brakes, but as if it had plunged into a pool of cosmic molasses, a gravitational quicksand that thickens with every inch of descent. This is the grand illusion of general relativity, a cosmic magic trick performed with the very fabric of existence. Gravity in its most extreme form does not just bend space, it warps time itself. Close to the black hole, the river of time flows sluggishly, while for your distant friend it continues its inexorable rush forward. Every tick of their clock corresponds to a smaller and smaller fraction of a second for you. From their perspective, your final desperate millimetre of progress toward the horizon takes a year. The next micron takes a century, the next nanometre an eternity. You are caught in a gravitational stasis, trapped in the amber of distorted space-time. Simultaneously, another equally bizarre transformation is taking place. The light from your superheated, glowing remains must fight its way out of the black hole's immense gravitational well to reach your friend's telescope. This is an uphill battle against the curvature of the universe itself. With every photon that escapes, a price is paid. Energy is stolen from the light, stretching its wavelength, shifting its colour. This is gravitational redshift, the universe's way of sapping the strength from a dying message. The brilliant blues and searing whites of your plasma stream signals of immense heat and violence begin to dim and redden. Through that distant lens, your fiery trail shifts from a celestial blowtorch to a desperate burning orange. Then, over agonizingly long periods, it cools further, becoming a blood-deep crimson, the colour of a fading ember. The light becomes weaker, the signal more tenuous. Your friend watches as your spectral ghost, once a brilliant streak against the abyss, is stretched and drained of its energy, fading like a photograph left in the sun. After what might be thousands of years from their perspective, the last visible photons will struggle free, arriving as faint infrared whispers. Then nothing. Your atoms, your very essence, will appear to be frozen forever at the edge of the event horizon, a final, silent two-dimensional painting plastered against the abyss. You will become a permanent phantasmal afterimage, a ghostly sentinel at the gates of hell, never quite falling in, never able to escape. A perpetual static monument to the place where the laws of physics break down. For the rest of time, from the viewpoint of every star and every galaxy, you are a part of the horizon, a frozen tableau of a journey's end. But that is their story. It is not yours. For you, for the disassembled consciousness now encoded in this stream of fundamental particles, there is no slowing down. There is no gentle fade to black. There is only the fall. You do not feel time dilating. Your internal clock, whether it is the decay of a radioactive isotope in your atoms, or the vibration of a quark, ticks on as it always has. 1 second for you is still 1 second for you. It is the universe outside that has gone mad, its clock accelerating to an infinite speed. As you plunge downwards, the entire future history of the cosmos flashes past in the light that falls in with you. You witness the birth and death of stars in the blink of an eye. Galaxies evolve, collide and decay in the time it takes to draw a breath you no longer have. The universe ages, cools and dies in a final brilliant flash of blue-shifted light that funnels into the abyss behind you. The event horizon, that boundary that seems so absolute to an outsider, is for you a place of no particular significance. It is not a wall, it is not a membrane. There is no signpost that reads, "You are now entering the black hole." You cross it. You simply fall through the geometric line that separates the world of maybe from the world of must. 1 moment escape was in principle possible. The next moment it is not, and you feel absolutely nothing to mark the transition. The fall continues unabated, relentless. The downward path is all there is. The plunge into darkness is swift, brutal, and utterly final. The universe saw you freeze, but you experienced an unbroken, terrifying acceleration into the heart of the maelstrom. Two realities born from a single event, forever unable to reconcile. One frozen in time, the other consumed by it. And here in this grand cosmic paradox lies yet another layer of complexity, another twist in the journey that depends entirely on the nature of the beast you have encountered. For not all black holes are created equal. The story we have just told of a violent external shredding followed by a fall into the abyss is the story of a stellar mass black hole. These are the common piranhas of the cosmic ocean. Born from the collapse of a single massive star, they are relatively small, perhaps only a few dozen miles across. Their diminutive size concentrates their gravitational gradient into a ferociously steep curve. For these celestial monsters, the tidal forces, the stretching and squeezing we call spaghettification, become lethal long before you ever reach the event horizon. They are cosmic butchers that tear you apart out in the open in full view of the universe before swallowing your constituent pieces. The destruction is the prelude to the fall. You are disassembled first, and only then does your atomic stream cross that final threshold, fading from outside view as it plunges toward the singularity within. This is the fate that awaits any traveller unlucky enough to wander too close to these ubiquitous, violent remnants of dead stars. But there is another kind of monster in the dark, vastly larger, ancient, and in some ways far more insidious. These are the supermassive black holes, the silent gravitational anchors around which entire galaxies spin. They are not born from a single star, but have grown over billions of years, devouring millions, even billions of suns, gas clouds, and other black holes. They are incomprehensible leviathans with event horizons that can be larger than our entire solar system. And it is here in the face of such scale that the nature of your fall changes completely. A supermassive black hole is so immense, so titanically vast, that the curvature of space-time at its edge is surprisingly gentle. The gravitational gradient, the difference in pull between your head and your feet, is almost negligible as you approach the event horizon. Its tidal forces are like the slow, gentle swells of a deep ocean, not the crashing, violent waves of a shallow shore. This leads to a possibility so profound, so utterly terrifying, that it stands as one of the most chilling concepts in all of science. If you fall into a supermassive black hole, you can cross the event horizon completely intact. There is no spaghettification, not yet. Imagine it. You're an astronaut adrift, your trajectory sealed. You float toward the great darkness, a sphere of perfect blackness that swallows the stars behind it. You feel no pain. You feel no stretching. You feel only the gentle, persistent tug of gravity, a silent and inexorable pull forward. Your ship's instruments might register the bizarre warping of space-time, but your body gives you no such warning. You look out of your viewport. The light from the universe behind you begins to warp and distort the starfield, compressing into a smaller and smaller window, as if you are looking out the back of a speeding train. But you are whole. You are still you. And then you cross. You pass through the event horizon, that one-way membrane in the fabric of reality. The window to the universe behind you snaps shut. All light, all information, all possibility of escape is now gone. You're inside, a ghost in the machine. A message in a bottle thrown into an ocean with no shores. From the perspective of your distant friend, the story remains the same. Your ship appears to slow redshift and freeze at the horizon for all eternity. But for you, the reality is a new and unique kind of horror. You're alive and conscious in a place from which you can never leave, and from which no word of your fate can ever be sent. You're sealed within a private universe of falling, a bubble of space-time disconnected from everything that ever was or will be. The laws of physics inside this bubble have one single, terrifying rule. All paths, all possible futures lead in only one direction. Down. The singularity, the point of infinite density at the centre, is no longer a place in space. It has become an event in time. It is your future. Just as you cannot avoid next Tuesday on Earth, you cannot avoid hitting the singularity inside a black hole. It is the end of time itself, and it is coming for you. And the spaghettification, that brutal body-shredding force we thought you had escaped, it has not been avoided. It has merely been postponed. As you continue your silent fall through the internal warped dimension of the black hole, the gravitational gradients will begin to steepen once more. The gentle pull will become a firm grip, then a violent wrench. Deep within the hidden interior, far from the prying eyes of any possible observer, the tidal forces will finally find you. The stretching will begin. The universe's most violent act will be carried out in the dark, a final secret execution. You will be unmade, just as you would have been in a stellar mass black hole, but you will have been granted the chilling privilege of being conscious and whole as you pass the point of no return. You were given a moment of quiet passage into the prison, a brief deceptive calm before the inevitable sentence was carried out. So the downward path is not a single story, but a choice of fates. Do you meet your end violently torn asunder for the universe to see before your remnants are swallowed, or do you slip quietly behind the curtain hole and aware only to face that same dismemberment alone in the absolute inescapable privacy of eternity's prison? Either way, your constituent parts are now inside, disconnected from the cosmos. You have become pure information trapped on a collision course with the ultimate unknown, a place where our physics, our language and our imagination finally and completely fail, a place we can only call the singularity. The light is gone, all of it, not just dimmed or redshifted into oblivion, but fundamentally absent. The very concept of direction has been annihilated, folded into a single inescapable vector pointing forward. There is no longer a you and a destination, there is only the fall. Every particle of your being, every atom that once looked up at the stars is now a slave to a gradient of space-time so steep it has become a precipice with no bottom. The tidal forces you endured, that terrible stretching, was merely the overture. Now the symphony of destruction plays its final silent chord, pulling you into the heart of the enigma. Ahead of you lies not a place, but a verdict. An end point of space-time itself, a concept our mathematics calls the singularity. This is the destination you can never reach, yet cannot possibly avoid. It is a point that is not a point, a moment that is the end of all moments. To even speak of it is to use a language of ghosts. General relativity, Einstein's magnificent tapestry of gravity, space and time, which has guided us flawlessly across the cosmos, simply stops here. It offers up an answer of infinity and falls silent like a prophet struck dumb before their own god. Infinite density, infinite curvature of space-time. These are not descriptions of a physical object. They are the universe's error message, a signpost pointing to a realm where our most profound laws are null and void. Imagine all the mass of a star, or millions of stars, or even billions crushed. Not just into a small volume, but into a volume of zero. It is a mathematical impossibility that exists a tear in the very fabric of reality where the loom itself is broken. Here the distinction between space and time dissolves completely. The future is not a direction you travel in. It is a physical location you are being dragged towards. It is the crunch, the ultimate final and absolute end. And in that end we confront the greatest crime in the cosmos. For everything you are, every memory, every unique arrangement of atoms that constituted your life is information. Physics at its quantum core has a sacred, unbreakable law. Information can never be destroyed. It can be scrambled like burning a book. The letters turn to ash and smoke, but in principle, if you could track every single particle, every photon of heat, you could reconstruct the original text. The universe, we believe, never truly forgets. It is a perfect record keeper. Yet the black hole presents us with a paradox so profound, it has haunted physicists for half a century. As you are compressed into the singularity, what happens to the information that is uniquely you? General relativity provides a chillingly simple answer: it is gone. Annihilated. Wiped from the cosmic ledger forever. The library of the universe has just had a book irrevocably burned its contents, lost to eternity. This is the black hole information paradox. It represents a fundamental schism in our understanding of the universe, a violent clash between our two great pillars of physics. On one side stands Einstein's relativity governing the grand tapestry of the cosmos, which insists the information is locked away, and ultimately destroyed inside the singularity. On the other stands quantum mechanics, the strange and powerful rules of the subatomic world which declares with absolute certainty that the total information of a closed system must be conserved. They cannot both be right. For decades, this contradiction festered at the heart of physics. Then a breakthrough came from an unexpected quarter. Stephen Hawking, contemplating the quantum world at the edge of the event horizon, realized that black holes are not perfectly black. They should glow. He discovered that due to quantum fluctuations in the vacuum of space, pairs of virtual particles are constantly popping into and out of existence. When this happens at the very lip of the event horizon, it's possible for one particle to fall in while its partner escapes. The escaping particle becomes real, stealing a tiny fraction of the black hole's mass energy to do so. Over unimaginable timescales, trillions upon trillions of years and more, this steady leak of what we now call Hawking radiation causes the black hole to evaporate. It slowly shrinks, losing mass, until in a final brilliant flash of energy, it disappears completely. And here the paradox returns with a vengeance. If the black hole evaporates, and the information that fell inside is truly gone, then the universe has committed its ultimate crime. It has forgotten something. The law of quantum mechanics has been violated. Hawking himself initially believed the information was truly lost, a concession that shook the foundations of science. If information can be lost in a black hole, perhaps it can be lost elsewhere too. The predictable clockwork universe we thought we understood might be fundamentally unpredictable, with reality itself flickering in and out of existence. But the quantum physicists refused to yield. They argued the information must get out. Perhaps it is subtly encoded in the escaping Hawking radiation. Imagine your essence, your memories, your very being not destroyed, but shredded and imprinted on this faint, chaotic thermal glow. Each escaping particle would carry a tiny, almost imperceptible correlation to the particles that fell in before it. Reconstructing you from this cosmic static would be infinitely harder than reassembling a book from smoke and ash, but according to quantum theory it must be possible. The universe, they insisted, does not cheat. This fierce debate has led us to an even more terrifying and bizarre possibility, a potential resolution known as the firewall paradox. The argument is subtle, but its implications are violent. To preserve the laws of quantum mechanics, a delicate link must be maintained between the escaping Hawking radiation and the interior of the black hole. This link is based on a strange quantum property called entanglement, a connection between particles that persists no matter how far apart they are. But there's a problem. Quantum mechanics also dictates that a particle can only be fully entangled with one other partner at a time, a rule known as monogamy of entanglement. The escaping radiation particle needs to be entangled with all the radiation that came before it to carry out the information, but it also needs to be entangled with its twin that fell into the black hole. It cannot do both. The universe is forced to make a choice. To solve this paradox, some physicists proposed a radical, terrifying solution. Perhaps the moment a particle crosses the event horizon, the violent needs of quantum mechanics force the entanglement with its infalling partner to be catastrophically severed. Breaking this quantum bond would not be a gentle process. It would release an enormous amount of energy. The consequence would be a shell of superheated high-energy particles erupting into existence precisely at the event horizon. A wall of fire, a quantum tripwire incinerating anything that attempts to cross. In this scenario, your journey would have ended far earlier than you ever imagined. You would never reach the singularity. You wouldn't even make it inside the black hole. The instant you touch the horizon, you would be vaporized by a curtain of pure energy, your information instantly thermalized and ready to be radiated back out into the cosmos. The calm, mathematically pure event horizon we described earlier would be a lie. It would instead be the most violent boundary in the universe, a celestial blowtorch guarding the entrance to infinity. This idea is profoundly unsettling, as it violates another cornerstone of physics, Einstein's equivalence principle, the very idea that falling freely is indistinguishable from floating in empty space. An astronaut crossing the horizon should by all rights feel nothing special. A firewall would mean they feel everything all at once in a final agonizing blaze. We are left with a trilemma, a choice between three impossible options: Either information is lost violating quantum mechanics, or the equivalence principle fails and a firewall exists violating general relativity. Or there is some other even stranger physics at play that we haven't even begun to comprehend. The truth is, we are trying to read a message written in a language we do not speak. The singularity is where gravity, the force of the macrocosm, becomes so intense that it crushes matter down to the scale of the microcosm, the realm of quantum mechanics. To understand what happens here, we need a dictionary that can translate between these two languages. We need a theory of quantum gravity. This is the holy grail of modern physics, a single framework that can describe the universe at all scales, from the spin of an electron to the collision of galaxies. Theories like string theory propose that at the fundamental level, particles are not points, but tiny vibrating strings, and the singularity might be a chaotic, ultra-dense tangle of these strings. Other ideas, like loop quantum gravity, suggest that space-time itself is made of discrete, indivisible chunks, and the singularity is where you can go no further because you have reached the fundamental atom of space and time. These ideas are at the very frontier of human knowledge, magnificent mathematical structures built to peer into an abyss we can never directly observe. They tell us that the singularity might not be an endpoint of infinite density, but a transition point. Perhaps it is not a dead end, but a gateway. Could the matter and information crushed into this point rebound, giving birth to a new universe inside the black hole? Is it possible that our own universe began from just such a singularity, the remnant of a star that collapsed in some greater older cosmos? The black hole then would not be a tomb but a cosmic womb, a place where universes are born. Or perhaps the singularity is something even stranger, a place where time doesn't just stop but loops back on itself, or a point where our three spatial dimensions connect to others, a true portal in the fabric of reality. We stand at the edge of this ultimate question, armed with equations that break and theories that tremble. What is the final fate of the matter that dares this journey? Is it obliterated, its story erased from the cosmic narrative forever? Is it incinerated at the edge, its information violently recycled back into the universe? Or is it transformed, planted like a seed in the soil of a new creation, its complex information blossoming into a new reality with its own stars, its own galaxies, its own life? The singularity holds the answer. It is the point where our physics ends, but where the universe's story may just be beginning again. It is the ultimate boundary not just of space and time, but of our own understanding. We have fallen into the question mark at the center of everything, and the silence that greets us is not empty. It is filled with the weight of all the possibilities we have yet to imagine. The final truth about what lies in the heart of a black hole may not just rewrite our understanding of gravity, it may force us to redefine what we mean by space, by time, and by reality itself. And so here at the precipice of infinity, our journey reaches its inevitable, unknowable end. You have crossed the final threshold, a traveller dissolved into the very grammar of the universe, your constituent atoms now part of a mystery that transcends space and time as we comprehend them. The singularity is not a destination in any conventional sense. It is a full stop at the end of reality's sentence, a place where the laws of physics, our trusted guides through the cosmos, finally fall silent, their voices lost in an impossible roar of infinite density. This is not just the end of your fall. It is the end of the path itself, a point beyond which the map is not merely blank, but utterly inconceivable, a concept torn from the fabric of logic. We began this descent together, propelled by a curiosity as powerful as gravity itself. We sought to understand what it would truly mean to fall into a black hole, to undertake the one-way journey into the universe's ultimate abyss. It started as a silent, almost serene surrender to the inevitable, a cosmic tide pulling you gently from the familiar shores of your own spacecraft. From that vantage point, the black hole was a perfect circle of nothing, a hole punched in the starfield, deceptively calm, its true nature veiled by the elegant simplicity of the event horizon. That boundary once crossed sealed your fate more completely than any prison wall ever conceived. It was the moment space-time itself turned against you, the future becoming a physical direction, a path leading only inward toward a single, inescapable point. We witnessed how the universe you left behind would accelerate into a fast-forwarded frenzy, its entire future history, the birth of new stars, the death of galaxies, the final cooling of the cosmos itself, flashing before your eyes. In a fleeting instant, a final blue-shifted message from a world to which you could never return. Inside, your reality became a strange and hostile geometry. The gentle pull became a relentless tidal force, a cosmic inquisitor intent on discovering your breaking point. We watched through the lens of physics as that force seized you as the difference in gravitational pull between your head and your feet, infinitesimally small, at first grew to become an irresistible, monstrous power. This was spaghettification, a term almost comical in its description of a fate so utterly terrifying. It is a process of deconstruction at the most fundamental level. Your body, a marvel of biological engineering, a vessel that carried your consciousness across interstellar voids, was elongated, stretched, and ultimately atomized by the raw curvature of space-time. In less than a tenth of a second, in that final violent moment before the singularity, you were not simply killed. You were unwritten. The complex arrangement of particles that constituted your thoughts, your memories, your very being was pulled apart and streamlined into a river of fundamental particles flowing into the infinite. This is the raw, unvarnished truth that lies at the heart of a black hole's darkness. It is a place of absolute transformation, where matter and energy are returned to their most elemental state, crushed under the weight of a collapsed star. Yet your terrifying hypothetical demise was not in vain. This journey from the silent approach to the violent atomic dissolution serves as the most extreme test imaginable for our understanding of the universe. For a century, we have been guided by Albert Einstein's theory of general relativity, a conceptual framework of such profound beauty and predictive power that it has become the bedrock of modern cosmology. It is a theory that describes gravity not as a force, but as the very shape of the universe, a dynamic four-dimensional fabric that can be warped, bent, and rippled by the presence of mass and energy. Everything we have witnessed on our fall, the bending of starlight around the black hole, the inexorable pull of the event horizon, the time dilation that separated you from the rest of us, and even the brutal mechanics of spaghettification, is a direct, spectacular confirmation of Einstein's genius. General relativity is the masterful symphony that describes the grand cosmic dance of planets, stars, and galaxies. It predicted the existence of black holes long before we ever saw one describing these gravitational prisons with unerring mathematical accuracy. It foresaw the subtle wobble in Mercury's orbit, explained the gravitational lensing that turns distant galaxies into ethereal arcs of light, and even predicted the existence of gravitational waves, those faint ripples in the fabric of reality 100 years before our technology was sensitive enough to finally hear the universe whispering to us. On this journey, we have seen Einstein's theory perform flawlessly in the most extreme environment we can imagine. It has been our reliable map through a landscape of warped space and twisted time, guiding us right up to the very edge of the abyss. But it is here at the heart of the black hole, in the crushing confines of the singularity, that the symphony finally breaks down. The music stops. The mathematics of general relativity, so elegant and powerful everywhere else, produces only infinity's infinite density, infinite gravity, infinite space-time curvature. These are not descriptions of a physical reality. They are mathematical cries for help. They are the equivalent of a calculator screen flashing error. It is the clearest signal the universe could possibly send us that our most profound theory of the large, our guide to the cosmic scale, is incomplete. Einstein's masterpiece, for all its glory, does not have the final word. It has led us to the edge of the cliff, but it cannot tell us what lies in the chasm below. This failure is not a defeat. It is a magnificent opportunity. It is the frontier of human knowledge, the point where our current understanding ends and a new, deeper reality must begin. The singularity is a gateway not just for the matter and light that fall into it, but for our own scientific imagination. It tells us that to comprehend the heart of a black hole, we need a new kind of physics, a theory that can bridge the greatest divide in all of science. This is the chasm that separates the world of the very large from the world of the very small. It is the conceptual gulf between the two great pillars of 20th century physics, general relativity, the theory of gravity, and the cosmos and quantum mechanics, the theory of particles probabilities and the subatomic realm. These two theories are spectacularly successful in their own domains. General relativity reigns supreme over planets, stars, and the expanding universe. Quantum mechanics provides a breathtakingly accurate description of the forces and particles that govern atoms and their constituents. For most of the universe's history, and in most places within it, these two great theoretical empires have been able to exist in a state of peaceful separation, each ruling its own scale without conflict. But in the extreme conditions of the singularity, these two worlds are forced to collide. Here, an immense star-crushing mass is compressed into a space smaller than an atom. It is a realm that is simultaneously infinitesimally small and unbelievably massive. It is both a quantum object and a gravitational behemoth. To describe it, you need both theories at once, and when you try to apply them together, they declare war. They give us contradictory answers. Mathematical nonsense, a universe that is fundamentally paradoxical. This is the central crisis of modern theoretical physics, and the singularity of a black hole is its most dramatic battleground. The resolution to this conflict, the peace treaty between the titanic and the tiny, is what physicists call a theory of quantum gravity. This is the holy grail of modern science, a single unified framework that could describe all the forces of nature from the whisper of a photon to the collision of galaxies within one set of elegant and consistent equations. It would be the final chapter in a story that began with Newton, was rewritten by Einstein, and now awaits its next great protagonist. The search for this ultimate theory is the great intellectual adventure of our time, and physicists are exploring several tantalizing though unproven paths. One of the most famous is string theory, which proposes a radical reimagining of reality's fundamental ingredients. It suggests that if you could zoom in on an electron or a quark with unimaginable magnification, you would find not a point-like particle, but a tiny vibrating filament of energy, a string. The different ways this string can vibrate, like the different notes produced by a violin string, correspond to all the different fundamental particles we see in the universe. In this view, the rich tapestry of matter and energy that surrounds us is nothing more than a cosmic symphony played on these infinitesimal strings. String theory is mathematically beautiful and conceptually audacious. It requires a universe with more than the 3 dimensions of space, and one of time that we are familiar with, perhaps as many as 10 or 11 dimensions in total, with the extra ones curled up so tightly that they are imperceptible to us. Within its complex framework, gravity arises naturally not as a separate force, but as another vibration of these fundamental strings. It offers the tantalizing prospect of a theory where gravity and quantum mechanics are no longer at odds, but are instead 2 different facets of a single deeper reality. It suggests that inside a black hole, the singularity might be resolved with the infinite point replaced by a fuzzball of strings, a bizarre multi-dimensional object that encodes all the information that ever fell in. Another leading contender is loop quantum gravity. This theory takes a different approach, focusing not on the particles within spacetime, but on the nature of spacetime itself. It proposes that the smooth continuous fabric of reality described by Einstein is actually an illusion. Just as a piece of cloth is woven from individual threads, loop quantum gravity suggests that spacetime is built from discrete, indivisible chunks, or quanta, of space and time. These are the fundamental atoms of geometry, the smallest possible volume, the shortest possible duration. At this foundational level, spacetime is not a smooth stage, but a dynamic, evolving network of connections, a cosmic web of finite loops. According to this idea, you cannot squeeze matter into an infinitely small point, because there is no such thing as an infinitely small point. There is a fundamental pixel size to reality. As a star collapses to form a black hole, it can only be compressed so far before it reaches this fundamental limit, this smallest possible unit of space. At that moment, the inward crush of gravity would be met by an outward quantum pressure of spacetime itself, a repulsive force that prevents the formation of a true singularity. Instead of collapsing to infinity, the matter would bounce, creating what some have called a Planck star. This bounce could potentially create a tunnel through spacetime, a wormhole leading to another part of our universe, or perhaps even to another universe entirely. It is a mind-bending possibility suggesting that the end of your fall might not have been an end at all, but a violent and transformative rebirth into an unknown realm. These are just two of the leading ideas, each a profound and beautiful attempt to write the next chapter of our cosmic story. Whether the final answer lies in strings loops or some other idea we have not yet even conceived of, one thing is certain: black holes are not merely cosmic destroyers, they are the ultimate laboratories. They are nature's particle accelerators, crushing matter and energy under conditions so extreme they are far beyond our ability to replicate on Earth. They are gravitational crucibles, where the very laws of physics are pushed to their breaking point, and in their failure they reveal the clues we need to find a deeper, more complete theory. They are the gatekeepers to the quantum realm of gravity, challenging us to look beyond Einstein and imagine a new description of reality. This is perhaps their greatest legacy. These objects born from the death of massive stars serve as cosmic anchors for our imagination, forcing us to confront the deepest questions we can ask. What is space? What is time? Where did the information that defined you go after you crossed the event horizon? This last question, the black hole information paradox, remains one of the most vexing puzzles in all of science. Quantum mechanics insists that information can never be truly destroyed, while general relativity suggests that inside a black hole, it is lost from our universe forever. Solving this paradox is a key test for any potential theory of quantum gravity, as it touches upon the very nature of reality and existence. Our journey is over, but the great adventure of discovery is not. We have travelled to the edge of the known, to a place where the darkness is absolute, and the laws of nature are stretched to their limits and beyond. We have seen how the universe in its most violent and extreme manifestations holds the keys to its most subtle and fundamental secrets. The fall into a black hole is more than a story of destruction. It is a story of revelation. It is a testament to the power of human curiosity, which drives us to ask questions about places we can never go, to understand fates we can never experience, and to build theories that can grasp the unimaginable. The darkness of a black hole is not empty. It is filled with the promise of new knowledge, with the whispers of a more profound reality waiting to be discovered. It reminds us that the greatest treasures of the cosmos are not found in the bright light of stars, but in the deepest shadows at the very edge of our understanding. The universe is under no obligation to be simple or intuitive. Its deepest truths are often hidden within its most extreme paradoxes, and it is in grappling with these enigmas that we push ourselves forward, expanding not only our knowledge but also our very sense of what is possible. The abyss calls to us not as a final destination, but as the next frontier.